In cultivated crops, dormancy can be overcome by mimicking nature's way of breaking seed dormancy. In this lecture, we will look at the differences among these artificial methods of breaking dormancy in seeds. Some of the artificial means of breaking dormancy include scarification, stratification, embryo excision, light treatment, and phytohormone or chemical treatment. Scarification refers to any process designed to make the seed coat or testa more permeable to water and gases. This involves the weakening, opening, or otherwise altering the coat of a seed to encourage germination. Scarification is often done mechanically, chemically, and thermally. Mechanical scarification involves grinding or shaking the seeds with abrasives or sand to scarify seed coats. This rightmost panel demonstrates how you can mechanically grind seeds to weaken the seed coat. But you might want to rethink your strategy to break seed dormancy if you are planting thousands of seeds in the field. Obviously, you cannot grind your seeds one by one. As an alternative, you can pierce or nick the seed coat with a needle, as is pictured in the left. Nicking the seed coat to allow water and air to permeate the seed will help the seed germinate. But again, if you need thousands of seeds for planting, nicking the seeds one by one is not recommended. This slide shows the effects of mechanical piercing and hull removal on the germination of oat seeds at 20 degrees Celsius as measured after 10 days. Hull is an alternative name for seed coats of cereals like oats. We have here on the first column the number of oat accessions or genotype. The second column indicates the germination of each accession after 10 days at 20 degrees without piercing or removal of hull. The third and the fourth columns show germination in the same accessions after piercing of hulls with a needle or hull removal respectively. Germination of the intact seeds range from 10 to 77%. This range increased considerably after piercing or removal of the hulls. With hull piercing, germination rate increased to a range of 84 to 96%, while with hull removal, germination increased to a range of 78 to 98%. This data demonstrates that mechanical scarification by piercing or removal of hulls can break dormancy and improve germination. Unlike mechanical scarification, chemical scarification involves the treatment of seeds with chemical abrasives such as sulfuric acid, sodium hypochlorite, and hydrogen peroxide. This method is not commercially popular because the materials are hazardous to handle and the seeds must be thoroughly washed and dried after treatment. Because seeds are treated with harsh chemicals, there is a potential reduction in germination. As an alternative to acids, seeds can also be treated with enzymes such as cellulase and pectinase to degrade seed coats. We can also use organic solvents, including alcohol and acetone, to dissolve water-insoluble compounds in the seed coat. While chemical scarification can enhance germination, it invariably leads to seed injury due to the disruption of cells. This may lead to fungal invasion and mechanical injuries. Aside from mechanical and chemical means of scarifying seeds, we can also use thermal scarification. Thermal scarification refers to the treatment of seeds at high temperature to make the seed coat or testa more permeable to gases and water. This graph shows the effects of thermal scarification of seeds on the germination of Iliamna remota, pictured here in the left. This plant is endemic to Langham Island in Illinois. In 2012, the species was declared as state endangered. Seeds of Iliamna remota were treated for 1 minute with hot water at 70, 80, 90, and 100 degrees Celsius. This graph shows the germination of the thermally scarified seeds within 20 days, as indicated by the x-axis. As you can see, hot water treatment improved germination of the seeds. Germination of the untreated seeds is indicated by the line with the triangle here. Everything else represents germination of seeds that were thermally scarified. Among the treatments, scarification of seeds at 80 degrees Celsius produced the highest germination as indicated by this line with diamonds. This slide shows the effects of different durations of thermal scarification at 80 degrees on the germination of Iliamna remota seeds. The seeds were scarified at 80 degrees Celsius for 10, 20, 30, and 60 seconds. In this graph, we can see that seeds treated at 80 degrees Celsius for 20 minutes recorded the highest germination percentage as indicated by the line with the diamonds. Aside from scarification, seed dormancy can also be broken with stratification or pre-chilling. Stratification is a temperature preconditioning of seeds that already imbibe water in cool, moist conditions to promote germination. Stratification is mostly required in seeds of temperate crops like the loblolly pine. This panel on the left shows a mature loblolly pine. This graph shows the germination of loblolly pine after stratification for a variable number of days, specifically for 0, 15, 30, 45, and 60 days. The x-axis indicates the number of germination days, while the y-axis indicates germination percentage. From this graph, we can clearly see that stratification substantially improves seed germination compared to the control as indicated by this line here. Maximum seed germination after 60 days for non-stratified seeds was around 78%. In contrast, stratification improved germination up to 85%, with seeds stratified for 60 days reaching a maximum germination of 85% only after 11 to 12 days. Perhaps the fastest way to overcome dormancy in seeds is to excise or remove the embryo from the seed. Dormancy is the function of both seed coat and the embryo. In cases where dormancy is controlled by the seed coat, the removal of the seed coat permits the germination of the embryo. An example that we have here is the eastern redbud. This is a mature redbud in full bloom. Seeds of the eastern redbud were allowed to uptake water for 48 hours before excision of the embryo from the cotyledon or radical end. Panel B are the excised embryos, and panel C shows germination of all the excised embryos. This graph compares the germination of intact seeds of eastern redbud with isolated embryos. These are the data for the intact seeds, and these are the germination data for the excised embryos. Germination of intact seeds was highest when the seeds were stratified first, as indicated by this bar here. But with embryo excision, even without stratification, the embryos were able to germinate, as you can see in this bar here. As you can see, germination of the non-stratified embryos was even higher than that of intact stratified seeds. Overall, this data illustrates the effectivity of embryo excision in breaking dormancy in seeds of the eastern redbud. Light is also an effective means of breaking dormancy. Light properties, including intensity, quality or wavelength, and duration, affect the germination of seeds with endogenous dormancy. Light treatments to induce germination capitalizes on the requirement of seeds for these external stimuli. In natural conditions, light quantity and quality that are perceived by the seeds depend on the seed's position in the soil, vegetative covering, and the light absorption characteristics of the seed coat. Dormancy in lettuce seed can be broken down by exposure to red light with a 670 nanometer wavelength. If you want to review the effects of light on seed germination, please refer to Lecture 26. Last but not the least, we have plant hormones and chemical treatments. The ability of the plant hormones and other chemicals to promote germination by breaking dormancy in seeds is explained more thoroughly in Lectures 27 and 28. In general, however, abscisic acid and auxin, especially at high concentrations, will lend dormancy in seeds and prevent them from germinating. The phytohormones gibberellic acid, cytokinin, ethylene, and strigolactone can break dormancy and induce germination. The chemicals hydrogen peroxide, potassium nitrate, and thiourea also promote germination. In summary, dormancy in cultivated crops can be overcome by mimicking nature's way of breaking seed dormancy. There are several ways of artificially breaking dormancy, and this includes scarification, stratification, embryo excision, light treatment, and phytohormone and chemical treatments. Scarification refers to any mechanical, chemical, or thermal process of making the seed coat or testa more permeable to water and gases. Stratification refers to temperature preconditioning of imbibed seeds in cool, moist conditions to promote germination. Embryo excision refers to the removal of the seed coat, excision of the embryo, and culturing it in an artificial media to germinate. Light treatments to induce germination capitalizes on the requirement of seeds for these external stimuli to germinate. Specific plant hormones as well as chemicals known to stimulate germination can also be used to overcome seed dormancy.